Hey you guys, this is Mr. Millings, and in this video we are going to learn how to solve buffer solution problems using the Henderson-Hasselbalch equation. So let's jump right in and take a look at the Henderson-Hasselbalch equation, and then let's solve some problems using it. So before we start talking about the Henderson-Hasselbalch equation, we must first review the concept of a buffer solution. And in an earlier video, we learned that a buffer solution is a solution that can resist significant changes in pH upon the addition of a strong acid or a strong base. We said that buffer solutions are made by dissolving in water a weak acid along with the salt containing the weak acid's conjugate base. So whenever we have a solution where we dissolve a weak acid along with that weak acid's conjugate base, which is going to be usually bonded to some sort of metallic ion, we're going to have a buffer solution. A solution that if we add more strong acid or strong base to it, the pH is not going to significantly increase or decrease. And we talked a little bit about why that works and how that works in our video on buffer solutions. So what is the Henderson-Hasselbalch equation, and how can it be used to calculate several different variables relating to a buffer solution? Well, if we take a look right here, the Henderson-Hasselbalch equation was developed by these two gentlemen here, Lawrence Joseph Henderson and Carl Albert Hasselbalch, working independent of one another. We end up with this right here, the Henderson-Hasselbalch equation, which states that the pH of a buffer solution is going to be equal to the pKa plus the log of the molarity of our conjugate base divided by the molarity of our weak acid. And so once again, the Henderson-Hasselbalch equation is going to be the pH of our buffer solution equaling the negative log of our Ka value for our weak acid plus the log of the concentration of our conjugate base divided by the concentration of our weak acid. And we can use this formula that we see right here to calculate many different variables relating to a buffer solution. We can calculate the pH of a buffer solution. We can calculate the mass of conjugate base that must be added to a buffer solution to keep it a certain pH. We can also calculate the mass of the weak acid. And so we can use this formula here to really calculate all kinds of different variables relating to a buffer solution. So let's go ahead and use this formula now to solve several different buffer solution problems. In this example, it says to determine the pH of a buffer solution consisting of 0.75 molar acetic acid and 0.25 molar sodium acetate. And we're given the Ka value. It says the Ka value is 1.76 times 10 to the negative fifth. This Ka value is the equilibrium constant for our weak acid. And we can typically get our Ka values of different weak acids from Google. You can Google search Ka value of weak acids and a table of Ka values will pop up. So anytime you're asked to determine the pH of a buffer solution, when you're given the concentration of your weak acid and you're given the concentration of its conjugate base, but you're not given the Ka value, well, you're probably not going to be able to solve that problem, so you're going to need to go ahead and look at a table of Ka values to get the Ka value of your weak acid. So we have a buffer solution here that's been made by mixing 0.75 molar acetic acid with 0.25 molar sodium carbonate. And so if we take a look here, we can see that this right here is going to be our weak acid. And we can tell that this is our weak acid because it starts with hydrogen, and typically acids are going to start with hydrogen. And we know that this isn't a strong acid because it's not one of these 6 or 7 strong acids that you've been asked to memorize. And if it's not one of those strong acids, it's going to be a weak acid. So we have our weak acid here, and in fact this is going to be acetic acid. And so it looks like we're preparing this buffer solution by taking 0.75 molar acetic acid and mixing it with 0.25 molar sodium acetate. And so this right here is going to end up being our conjugate base. And so how do we know that this is our conjugate base? Well, if you remember in an earlier video, we learned about the Brunstad-Lowry model. And in the Brunstad-Lowry model, acids are H plus donors. And so if this is an acid here, it's going to end up donating an H plus. And if this loses an H plus, what we're going to be left with is C2H3O2 minus, bonded to some sort of metallic ion, in this case sodium. So here is our conjugate base. And so what we're asked to do is we're asked to determine what the pH of this buffer solution is going to end up being. And so anytime you're asked to calculate the pH of a buffer solution, you're probably going to have to use the Henderson-Hasselbalch equation, which is right here. So to get the pH of our buffer solution, we're going to have to take the pKa value plus the log of the molar concentration or molarity of our conjugate base. In this case here, our conjugate base is C2H3O2 minus. And we can see by looking at the subscripts here that we have 1 mole of sodium for every 1 mole of acetate in this compound that we have right here. So every 1 mole of this entire compound, we're going to have 1 mole of sodium ions, and we're going to have 1 mole of acetate ions dissolved in that water. So we're going to have acetate as our conjugate base, and we're going to divide this by the concentration of our weak acid. In this case, our weak acid is acetic acid, so C2H3O2. There we go. And so here is the formula that we're going to use to solve this problem. So what is this pKa here? Well, to get the pKa, it's simple. It's very similar to how we calculated the pH of a solution when we were given the hydronium or hydrogen ion concentration. To get the pKa, we're going to have to take the negative log of our Ka value. So to get the pKa, we're simply going to take the negative log of 1.76 times 10 to the negative fifth. And when we put this in our calculator, we'll take the negative log of 1.76 times 10 to the negative fifth. And if we use the correct number of sig figs, we're going to end up with 4.75. So here is our pKa value. And so now we can go ahead and place that right in here. So to get our pH, we're going to have to take 4.75 plus the log of the molarity of our conjugate base, which it tells us is 0.25 molar. So 0.25 divided by the molarity of our weak acid, which is 0.75. And so, once we plug this out into our calculator, when we take 4.75 plus the log of 0.25 divided by 0.75, we're going to end up with 4.27, a pH equal to 4.27. So we just calculated the pH of this buffer solution. The pH of our buffer solution is equal to 4.27. Now, does this answer make sense? Well, anytime the pH is less than pKa, which it is right here, we can see our pH is 4.27, our pKa is 4.75. This is typically going to be because the molarity of our weak acid is greater than the molarity of our conjugate base. So the pH is less than our pKa value because the concentration of our acid, in this case here HC2H3O2, is greater than the concentration of the conjugate base here, NaC2H3O2. And if we have more or a higher concentration of acid than we do base, this is typically going to cause a decrease in pH. So that is how we can use the Henderson-Hasselbalch equation to calculate the pH of a buffer solution. Let's take a look at another example using the Henderson-Hasselbalch equation. In this second example, it says to determine the pH of a buffer solution consisting of 0.75 molar ammonium chloride and 1.25 molar ammonia. And it tells us that the Kb value of our conjugate base is 1.8 times 10 to the negative fifth. So we have a weak acid. That's going to be this species right here, NH4Cl, mixed with the conjugate base, which is right here, our NH3. And so how can we tell that this is a weak acid and this is the conjugate base? Well, if you remember from an earlier video on the Brunstad-Lowry model, the weak acid is always going to have an extra H plus compared to the conjugate base. And so we're given the Kb value. We don't know the Ka value of our weak acid. We know the Kb value of our weak base. And you can typically find the Kb values not of our weak base, of our conjugate base, sorry. You can typically find the Kb value of conjugate bases on a table of some sort. And even if you can't find it in some table, you can calculate it. So let's take a look here. We're asked to determine the pH of a buffer solution consisting of 0.75 molar ammonium chloride and 1.25 molar ammonia. And so this looks like we're going to have to use the Henderson-Hasselbalch equation. The pH of this buffer solution is going to equal the pKa value plus the log of our conjugate base, which in this case here is NH3, the concentration of our conjugate base divided by the concentration of our weak acid, in this case here, ammonium chloride. So the problem is we don't know the Ka or the pKa. We don't know pKa. In fact, we don't even know Ka at this point. We're given the Kb value. So how can we find the pKa when we're given the Kb value? Well, let's first find the pKb. To get the pKb, and I'll go ahead and do this in red, to get our pKb, we simply take the negative log of our Kb value. So we'll take the negative log of 1.8 times 10 to the negative fifth. 1.8 times 10 to the negative fifth. And when we put this in our calculator, when we take the negative log of 1.8 times 10 to the negative fifth, we're going to end up with 4.7 if we use the correct number of sig figs here. So 4.7 is going to be our pKb. But how can we find pKa? Well, pKa plus pKb is always going to equal 14. And so if we're asked to find the pKa, we simply take 14 minus the pKb. So we'll take 14 minus 4.7, and we get 9.3. So our pKa value is right here, it's 9.3. And so we had to do all of this work just to plug it into right here. So the pH of this buffer solution is going to equal 9.3 plus the log of our conjugate base concentration, which it tells us is 1.25 molar, all divided by the concentration of our weak acid, which is 0.75 molar. And when we put this in our calculator, the pH of this solution is going to end up being 9.5. If we're using the correct number of sig figs, and there we go. So the pH of this buffer solution, consisting of 0.75 molar ammonium chloride and 1.25 molar NH3, is going to be approximately 9.5. And so does this answer make sense? Well, if we take a look here, our pH is greater this time than our pKa. And generally speaking, if the pH is greater than the pKa, that is going to be because the concentration of our conjugate base, in this case was NH3, is greater than the concentration of the weak acid, NH4Cl. So yeah, this answer seems to make sense. So that is how we can determine the pH of a buffer solution when we're given the Kb value. Let's take a look at another example. In this example, it says to determine the pH of a buffer solution consisting of 25.0 grams of HC2H3O2 and 45.0 grams of NaC2H3O2 in 625 milliliters of solution, and we're given the Ka value of our weak acid. It's 1.76 times 10 to the negative fifth. And so what makes this problem different than the example we did in number 1 is that we're given the mass of our weak acid and we're given the mass of our conjugate base that's bonded to this metallic ion right here. And we're asked to figure out what the pH of the buffer solution is going to be if these two masses of weak acid and conjugate base is added to 625 milliliters of solution. And so we have to do this problem slightly differently, and it's going to require a few more steps than we had to do in example problem number 1. But essentially we're asked to calculate the pH of a buffer solution, so we're going to have to use the Henderson-Hasselbalch equation. pH is going to equal the pKa plus the log of the concentration of our conjugate base, which in this case is going to be C2H3O2 minus, divided by the concentration of our acid, which in this case here is HC2H3O2. So let's first figure out what the pKa is going to be. To get the pKa, we're going to have to take the negative log of our Ka value. So we'll take the negative log of 1.76 times 10 to the negative fifth. And when we take the negative log of 1.76 times 10 to the negative fifth, negative log of 1.76 times 10 to the negative fifth is going to equal 4.75 as our pKa. So now we know what this is. However, we have to now figure out what the concentrations of our acetate ions are, and we have to figure out what the concentration of our weak acid is going to be first. So let's go ahead and figure out the concentration of our weak acid. Let's see here. We have 25.0 grams of HC2H3O2 we know that 1 mole of HC2H3O2 is going to be equal to 60.06 grams of HC2H3O2. And so this is going to give us 0.416 or 0.416 moles of this stuff right here, of C2 or HC2H3O2 minus. But we don't want to know the number of moles, we want to know the concentration or the molarity. So what we have to do now is carry this one step further. And what we have to end up doing is using our molarity equation, right? Or our molarity formula. We know that molarity is equal to moles per liter. So we have 0.416 moles. And how many liters of solution do we have? Well, it tells us we have 625 mLs. That's the same thing as 0.625 liters. And so when we put this in our calculator, 0.416 divided by 0.625, we're going to end up with a concentration of 0.666. 0.666 moles per liter, or a 0.66 molar solution of our weak acid. So now we need to do the same thing with our conjugate base. So if we take a look here, our conjugate base, it tells us we have 45.0 grams. Let's see if we are going to have enough room. We'll try it right here. We have 45. We'll go ahead and do this in a different color. We have 45.0 grams of our NaC2H3O2. We know 1 mole of NaC2H3O2 is going to have a mass of, let's figure this out, 22.99 plus 2 times carbon, which is 24.02, plus 3 times hydrogen for 3.03, plus 2 times oxygen, which is 16 for 32, is going to give us 82.04. Oops, not Na2, just simply Na C2H3O2. And when we put this in our calculator, I tell you what, let's just do this all in one step here. If we take a look, this step here is going to give us the number of moles of our sodium acetate. But we need to figure out the moles of just the conjugate base, which is our C2H3O2 minus ions. So we know by taking a look at this chemical formula here that 1 mole of this NaC2H3O2, when we dissolve it in water, is going to produce 1 mole of C2H3O2 minus ions, right? If we take a look at our chemical formula here, we have 1 mole of sodium ions and 1 mole of acetate ions for every 1 mole of NaC2H3O2 that's going to be dissolved in water. And so when we take 45.0 and we divide by 82.04, we're going to get 0.549 moles of our conjugate base C2H3O2 minus. But now we have to figure out the concentration. These brackets here mean concentration, so we're now going to have to calculate the molarity. And so to get the molarity of our conjugate base, we're going to have to take the number of moles and divide it by the liter of solution. So we end up with 0.549 divided by 0.625 liters. And when we take 0.549 divided by 0.625, we end up with 0.878. So the concentration of our conjugate base is going to end up being 0.878 molar. So we had to do all of this work first just to get the concentrations of our conjugate base and our weak acid. And so now we can plug these values into the Henderson-Hasselbalch equation here, and we can end up with our final answer. So let's go ahead and do that. To get the pH of this solution, we are going to have to take the pKa value, which we figured out was 4.75, plus the log of the concentration of our acetate ions, or our conjugate base, which was 0.878 molar, 0.878, all divided by the concentration of our weak acid, 0.666. And when we put this all in our calculator, we're going to end up with a pH of 4.87. And this right here is going to be our final answer. And so does this answer make sense? Well, if we take a look, the concentration of our weak, or our conjugate base, right? The concentration of our conjugate base is greater than the concentration of our weak acid, or in other words, the concentration of our weak acid is less than the concentration of our conjugate base. And if we take a look here, the pH is 4.87, so the pH here is going to end up being greater than the pKa value. And if the pH is greater than the pKa, which it is here, that is typically going to mean that the concentration of your conjugate base is going to be greater than the concentration of your weak acid, which in fact it is. So you know you probably did the problem correctly. So this is how we're going to calculate the pH of a buffer solution when we know the masses of the weak acid and the mass of the conjugate base and the volume of solution that it's in, and the Ka value should probably be given in that example problem. Let's take a look at another problem. In this fourth example problem, it says to determine the mass of NaC2H3O2 that must be added to 325 milliliters of a 0.75 molar acetic acid solution to form a buffer solution with a pH of 4.25, and we're given a Ka value of our weak acid 1.76 times 10 to the negative fifth. And so we have a buffer solution here. And if it didn't tell us that we had a buffer solution, we can tell this is a buffer solution because we have a weak acid here. Here is our weak acid. In fact, this is acetic acid. And if we take a look here, we have the conjugate base of our weak acid bonded to some sort of metallic ion. So here is our conjugate base right here. So we have to determine the pH. No, I'm sorry. If we take a look, we have to determine the mass of NaC2H3O2 that must be added to 325 milliliters of 0.75 molar acetic acid to form a buffer solution with a pH of 4.25. So in this problem here, we know the pH, right? We know the pH of this buffer solution. And usually when we're working with buffer solution problems, we're going to have to use the Henderson-Hasselbalch equation. So we know the pH, it's given as 4.25. We can figure out the pKa by taking the negative log of this, and we can figure out what the concentration is of our conjugate base, and from that we can then figure out the mass. So let's go ahead and figure this out. There's a lot that's happening here, but essentially we know that when we have a buffer solution, we're probably going to have to use the Henderson-Hasselbalch equation to make some calculations. So we have pH equaling the pKa plus the log of the concentration of our conjugate acid. And so what is our conjugate base. And so what is our conjugate base here? Well, if this donates an H+, what we're going to be left over with is C2H3O2-, and our acid here is going to be acetic acid, HC2, sorry about that, HC2H3O2. So what we're asked to figure out is the mass of our NaC2H3O2, and so to figure out the mass of our NaC2H3O2, we should probably first figure out the concentration of C2H3O2. If you keep in mind the molarity formula, molarity equals moles per liter. And so what we can then do is manipulate this formula to figure out the number of moles. To get the number of moles, we're going to have to take the molarity times the volume of our solution. So if we figure out if we figure out the molarity of our C2H3O2, we can then use that to determine the number of moles of this stuff there are, and then we can figure out the mass of this stuff right here. So here we go. Let's go ahead and do this. Let's first use a little bit of algebra. If we take a look, we need to solve for the concentration of C2H3O2-. And so the first step we're going to do is going to be to subtract pKa from both sides. So we'll end up with pH minus pKa equaling the log of the concentration of C2H3O2-, all divided by the concentration of our weak acid HC2H3O2. So how do we get rid of this log? Well, this is a base 10 log, and so what we can do is we can take 10 to the pH minus pKa, and if we take 10 to this right here, we're going to end up with simply the concentration of C2H3O2- all over the concentration of our acid, HC2H3O2. So we're trying to solve for this. We're running out of room, so I'll go ahead and put this up here. So if we multiply both sides by this right here, we'll be left with the concentration of our weak acid, HC2H3O2, times 10 to the pH minus pKa, and this is going to equal, let's make some room here, the concentration of our conjugate base, C2H3O2-. So once we find the molarity here, we can plug it into this formula here to figure out the number of moles. We can then figure out the number of moles of NaC2H3O2 and then figure out the mass. So let's go ahead and plug in some numbers here. What is the concentration of our weak acid? Well, it tells us that the concentration of our weak acid is going to be, or is, 0.75. So we have 0.75 here times 10 to the pH. What is our pH? Well, it tells us it's 4.25 minus the pKa. So how are we going to get the pKa? Well, to get the pKa, we're going to have to take the negative log of our Ka, which is equal to the negative log of 1.76 times 10 to the negative fifth. And when we put this in our calculator, we are going to end up with 4.75. So here is our pKa. We'll go ahead and put that right here, 4.75. And this is going to equal the concentration of our conjugate base, C2H3O2 minus. And so now when we put this in our calculator, we're going to end up with the concentration of our acetate ions, which is our conjugate base, equaling 0.237 molar, or 0.237 moles per liter. But this is not our final answer. This is just the concentration of our acetate ions. We're asked to figure out the mass of this entire thing right here, Na2C3 or NaC2H3O2. So now in our last step here, before we plug it into the molarity formula, is to figure out the number or the molarity of this right here. And so we have 0.237 moles of C2H3O2 minus for every 1 liter. If we take a look here, what is the ratio going to be of our C2H3O2 minus ions to this entire compound right here? It looks like we have a subscript of 1, so we have 1 acetate ion here. So we have 1 mole of C2H3O2 minus ions for every 1 mole of NaC2H3O2. And so this is going to equal 0.237 moles per liter, or molar NaC2H3O2. This is not our final answer. In our final step, what we're going to have to do is use this molarity formula right here. Molarity equals moles per liter. And so if we manipulate this formula, we're going to be left with moles equaling molarity over liters. And so what is the molarity of our NaC2H3O2? It's right here, 0.237 divided by the number of liters. Well, if we take a look, we have 325 milliliters, which is 0.325 liters. And when we put this in our calculator, 0.237 divided by 0.325, we're going to end up with 0.729 moles of NaC2H3O2. But you guessed it, this is not our final answer. We have to figure out the mass. So how can we figure this out? How can we convert moles to grams? We have to set up one last little problem here. And so we'll go ahead and do this right over here where we have a little bit of room left over. If we have 0.729 moles of NaC2H3O2, we know that 1 mole of NaC2H3O2 is going to be equal to how many grams? Well, let's figure this out. Sodium is 22.99. It looks like we have 2 carbons, so 2 times 12.01. We have 3 hydrogens, so 3 times 1.01. And we have 2 oxygens, so 2 times 16. And we're going to end up with 82.04 grams. So when we take 0.729, and we divide this by, we multiply by 82.04, we're going to end up with 59.8. And this right here is going to be our final answer. So there is a lot of work that's taken place here, but this right here is going to be our final answer. So it says to determine the mass of sodium acetate that must be added to 325 milliliters of a 0.75 molar acetic acid solution to form a buffer solution with a pH of 4.25. It looks like we're going to have to add 59.8 grams of our sodium acetate to this solution or this buffer solution in order to have a pH of 4.25. So a lot going on there, but that's how you're going to solve that little problem right there. So if you like what you see, go ahead and click that little bomb in the bottom right hand corner, and that will subscribe you to my channel. And feel free to leave any comments or questions in the comments section down below. And I really hope you guys found this helpful.